Right. Got a big test coming up, huh? Transformers and large language models want those concepts to really stick. Not just for the multiple choice, but for those written answers too, right?
Are gonna nail this.
Yeah, we are. We're going deep today. Think of this as your secret weapon for acing that
I'm gonna
exam.
make these ideas so clear you could explain them to anyone, even your grandma.
Exactly. And to help break it all down, we've got our expert guide right here. We've got articles, videos, the whole deal on everything from like the tech behind ChatGPT to how this stuff actually works.
Let's kick things off with a problem. The problem transformers were designed to solve. Older language models, they had a real tough time with sentences of different lengths.
Yeah.
Imagine trying to understand a story, but you can only remember like a few words at a time. You'd miss the whole plot.
Yeah, you'd be lost.
Traditional models were kind of stuck in that situation. They relied on these dense layers, needed a fixed size input.
So like trying to cram a whole novel into like a tiny tweet.
That's a great way to put it. Language just doesn't work that way, though. Sentences can be short, long, filled with clauses. It's a beautiful mess.
And that's where transformers come in to save the day.
Exactly. Transformers can handle this variability thanks to these things called attention layers. It's like a reader focusing on specific words, depending on their relationship to other words.
Okay.
Like, think of it like reading a mystery novel, right? You pay extra attention to clues that might be important later.
Okay, so the model's like a detective, piecing together the clues in the sentence. I like that.
That's a great way to remember it. This breakthrough, it came about in 2017. There's a paper called Attention is All You Need. Vaswani and their team really revolutionized how we process language.
Attention is all you need. Got to remember that one.
Yeah.
For the test. And maybe for life in general. So attention layers help transformers understand context. But what about like the actual words themselves?
Mhm.
How does the model deal with all the different words and their meanings?
That's where tokens come into play. They're like the building blocks of language for the model.
So each word gets its own token, like a little name tag.
Sometimes, but not always. Many models use something called subword tokenization. They break down words into smaller units.
Okay.
Imagine breaking down walking into walk in ing, right?
Okay.
This helps the model deal with a much larger vocabulary and the nuances of language.
Subword tokenization. That one sounds like a tricky test question. Okay, so the model breaks down words into these subword tokens.
Mhm.
But how does it keep track of all this information? Is there like a limit to how much it can handle at once?
There is. And that limit is determined by the context window, which is like the model's field of vision.
Yeah.
It determines how many tokens the model can consider at once. This ties into something called chunk size, which is the number of tokens processed together.
So the model takes a chunk of text, breaks it down into tokens,
Mm.
and then uses attention layers to understand how those tokens relate to each other within that chunk.
Mm.
But is there a limit to how big those chunks can be?
There is, and it comes down to computational resources. The calculations involved, they have this thing called quadratic complexity.
Quadratic complexity. That sounds a little intimidating.
Don't worry, it's not as scary as it sounds. Think of it like a square, right?
Okay.
The sides of the square represent the chunk size. If you double the chunk size, you're not just doubling the sides of the square, you're quadrupling its area. That's how computational resources scale with chunk size.
Oh, okay. So if the chunk size is n, the number of comparisons is n squared.
Exactly. Larger chunk sizes mean more memory and slower processing times. It's a trade-off.
Got it. So bigger chunks mean more context, but also more work for the model. Now I'm really curious about what happens inside the transformer block itself. What's going on in that mysterious black box?
Let's break it down. 3 key parts: embedding, transformer block, and output probabilities.
Okay.
Think of it as a 3-step recipe for AI magic.
AI magic, I love it. Let's start with embedding. What's the magic spell that transforms words into numbers?
It all starts with those token embeddings we talked about. Each token, it gets transformed into a numerical vector, kind of like its own secret code, capturing the word's meaning.
So it's like each word has its own, like, personality profile. In the model's world.
That's a great way to think about it. These personality profiles, they live in this high-dimensional space where similar words are clustered together.
Okay, so I've got these embeddings capturing the meaning of each word. But what about their position in the sentence? Doesn't that matter too?
Absolutely. That's where positional encoding comes in. Imagine it like giving each word an address in the sentence.
Okay.
It helps the model understand not just what's being said, but when it's said.
Ah, so the model knows the word order, not just the word meanings. That's a key point for the test, for sure. So we've got embeddings with meaning and position. What happens next in this transformer block adventure?
Now we get to the heart of it all. The transformer block itself. This is where the real magic happens. There are two key players here: multi-head self-attention and the multi-layer perceptron, or MLP. Think of them as like a dynamic duo working together to refine the token representations.
A dynamic duo. Sounds like a superhero team-up.
And just like in a comic book, there are multiple rounds. Several transformer blocks are stacked sequentially, refining the token representation with each layer. It's like reading a book chapter by chapter, building up a deeper understanding with each turn of the page.
Okay, let's break down these components one by one, starting with multi-head self-attention. What's so special about this attention mechanism?
Remember those attention layers we talked about? Well, multi-head self-attention is like having multiple spotlights shining on different parts of the sentence simultaneously.
Oh, okay.
Each spotlight is focusing on different relationships between the tokens, helping the model understand the context even better.
So the model's a master multitasker. Paying attention to multiple things at once, impressive.
Exactly. Now, to understand how it actually works, imagine a detective using keywords to search for information.
Right.
They have a query, what they're looking for, and they compare that to keys that represent different pieces of information.
Okay.
The closer the match, the more relevant that information is.
Okay, so the model's like a detective searching for clues, and the attention mechanism helps it find the most relevant information. I can picture that.
That's a great way to visualize it. This happens through something called dot products, which measure how well the query and key vectors align. The higher the dot product, the stronger the connection.
It's like a dating app for words, finding the best matches.
But hold on. If the model is looking at all these keys, how do we make sure it doesn't like peek ahead in the sentence and cheat?
That's a great question. That's where masking comes in. It's like putting blinders on the model so it can only see the words that came before. No peeking into the future. Masking. I'll definitely need to remember that one for the test. So the model gets these attention scores based on how well the query and key match up. What happens to those scores?
They get normalized using a function called softmax, which turns them into probabilities. Think of it like this. The model is saying, I'm this much certain that this word is related to this other word.
Probabilities. So it's not just saying yes or no about relationships. It's giving us a degree of certainty. That's pretty sophisticated.
Right. And softmax, it ensures that all those probabilities add up to 1, which is essential for making predictions.
Okay. So we've got these attention probabilities. What do we do with them?
We use them to weight the values. Remember those keys we talked about?
Yeah.
Each key has a corresponding value, which is the actual information associated with it.
Right. So the model's figuring out which values are most important based on the attention probabilities. It's like ranking the clues in a mystery novel.
Exactly. The values are multiplied by their corresponding attention weights and then summed up, creating this new vector that represents the token, now enriched with all this contextual information.
So it's like taking a blend of all the relevant information,
Right.
with the most important parts getting the most attention. This attention mechanism is really impressive. It's like the model is understanding the relationships between words just like a human reader would.
And remember, we're doing this with multiple attention heads in parallel, each focusing on different aspects of the relationships between tokens. It's like having like a whole team of expert readers, each bringing their own perspective to the table.
Okay, I'm starting to get a good grasp on multi-head self-attention. It's like a sophisticated matchmaking service for words, finding the most relevant connections and using those connections to build a richer understanding of the text.
You got it. That's the essence of how transformers capture context.
Amazing. But wait, there's another part to this transformer block, the multi-layer perceptron, MLP. What's its role in all this?
So while the attention mechanism is all about relationships between tokens, the MLP focuses on the individual tokens themselves.
Okay.
Think of it like this. The attention mechanism is like the social butterfly, connecting with everyone, while the MLP is like the deep thinker, focusing on the individual's unique qualities.
So the attention mechanism's the networker, and the MLP's the philosopher. I like it. But what does the MLP actually do?
It processes each token through a series of mathematical operations, kind of like putting it through a training course to enhance its representation. It goes to a higher dimension,
Right.
which you can think of as expanding its vocabulary, and then back down to the original dimension.
Why does it need to go to a higher dimension and then back down?
Think of it like this. Going to a higher dimension gives the model more room to maneuver. It's like expanding your vocabulary so you can express more nuanced ideas, and then bringing it back down ensures compatibility with the rest of the network.
So the MLP is like a language coach, helping the model express itself more eloquently.
Exactly. And together, multi-head self-attention and the MLP, they make a powerful team,
Hmm.
allowing transformers to learn these complex relationships and really capture the beauty of human language.
This transformer block is truly a marvel of engineering. It's like a symphony of mathematical operations, orchestrated to extract meaning from text. But wait, we haven't even gotten to the model's output yet, have we? What happens after all this processing in the transformer block?
You're right, there's still one more step. Remember, the whole point of a language model is to predict the next word in a sequence. So we need to take those processed embeddings and turn them into something that represents words again.
So it's like translating the model's secret code back into plain English.
That's a great way to think about it. The output probabilities layer does just that. It takes the final embedding vector for each token and transforms it into a vector of probabilities. Each entry in this vector, it represents the likelihood of a particular token being the next word in the sequence.
So the model is saying, based on everything I know about this sentence so far, here are my best guesses for what comes next.
Exactly. It's like the model is trying to finish your sentences for you. And to ensure those guesses are valid probabilities, meaning they all fall between 0 and 1 and add up to 1, we use the trusty softmax function again. Remember that.
Softmax to the rescue. It seems like that function is the superhero of this whole transformer architecture.
It really is a crucial component, making sure the model's outputs are interpretable and meaningful.
Okay, so we've got these output probabilities. What happens next? How does the model actually choose the next word? Does it always go with the highest probability?
That's where things get really interesting. The model doesn't always pick the word with the highest probability. Sometimes it throws in a bit of randomness, just to keep things interesting.
Randomness. Why would we want the model to be random? Wouldn't that make it less accurate?
Not necessarily. If the model always chose the most likely word, its output would be very predictable and honestly, a bit boring. Randomness helps the model explore different possibilities and generate more creative and surprising text.
So it's like adding a pinch of spice to the recipe.
Exactly. And the amount of randomness is controlled by a parameter called temperature.
Temperature, like how hot the model is running.
Not quite, but it's a good analogy. Think of it like this. A lower temperature makes the model more predictable, like a simmering pot, while a higher temperature introduces more randomness, like a rolling boil.
So if we want the model to be more creative, we turn up the heat. I'm loving these analogies. They're making these concepts so much easier to remember.
That's the goal. We want you to walk out of that test feeling like a transformer expert.
Okay, I think I'm starting to see how all these pieces fit together. The model takes in text, breaks it down into tokens, embeds those tokens with meaning and position, processes them through the transformer block with its multi-head, self-attention, and MLP, and then outputs probabilities for the next word with a dash of randomness controlled by temperature. That's quite a journey.
That's a great summary. And remember, this whole process happens for every single word the model generates.
Whoa, that's a lot of computation going on behind the scenes. No wonder these language models need so much processing power.
It's true, but the results are remarkable. Transformers have really revolutionized natural language processing, allowing us to build models that can generate human-quality text, translate languages, answer questions, and so much more.
It's incredible. And the fact that it's all based on these relatively simple mathematical operations is even more mind-blowing.
It's amazing what you can achieve with a bit of math and a lot of ingenuity.
Well said. But wait, we're not quite done with the transformer block yet, are we? You mentioned something about dropout and residual connections.
Ah, yes. Those are two important techniques that help improve the model's performance.
But for the sake of this deep dive and my upcoming test, do we need to go into detail about those right now?
For a basic understanding, you can focus on the core concepts we've already covered. But if you're curious...
I am. Knowledge is power, as they say.
All right, then let's dive in. Dropout is a technique that helps prevent overfitting. Imagine studying for a test and only focusing on a few specific examples.
Okay.
You might do well on those examples, but you won't be prepared for the variety of questions that could be on the actual test, right?
So it's like studying too narrowly.
Exactly. Dropout prevents this by randomly dropping out some of the neurons during training. This forces the model to learn more generalizable features that can apply to a wider range of inputs. It's like shaking things up, making sure the model doesn't get too comfortable with any one solution.
Got it. So dropout helps the model be more flexible. And what about residual connections? Those sounded pretty intriguing too.
Residual connections, they're like shortcuts that allow information to flow more easily through the network. This is particularly important for very deep networks, where the gradients can vanish as they travel back through the layers, making it hard to train the earlier layers.
Vanishing gradients. That sounds a bit spooky.
It just means that the signal gets weaker and weaker as it travels back through the network, like a whisper fading into silence. Residual connections, they act like amplifiers, boosting the signal so it can reach all parts of the network.
Ah, so residual connections are like those repeaters they use for long-distance phone calls, making sure the signal doesn't get lost along the way.
Exactly. They allow the gradients to bypass some of the layers, ensuring that even the early layers get enough feedback during training.
Okay, so dropout prevents overfitting and residual connections help with training deep networks. Those are some clever tricks.
They are, and they contribute significantly to the success of transformers.
Well, I think we've covered the transformer block in great detail. We've seen how it takes tokens and uses this incredible combination of attention mechanisms, MLPs, dropout, and residual connections to extract meaning from text. Now, I'm curious about how we actually train these models and what we can do with them once they're trained. Can we move on to the training process now?
Absolutely. Let's talk about how these models learn. So I've got this amazing transformer architecture, all set up, ready to go, but how do we actually teach it to understand language? What's the secret ingredient that turns this complex machinery into a language whiz?
It's got to be something special. Is there some secret formula like a magic potion or something?
The secret ingredient is actually pretty simple: data.
Okay.
And lots of it. We train transformers on massive amounts of text, like books, articles, websites, code, you name it. Imagine feeding the model, like a giant buffet of words and sentences, letting it feast on all that information.
So it's like the model is going to, like language school, immersing itself in all sorts of different texts.
Yeah. Exactly. The more data we feed it, the better it gets at recognizing patterns and understanding the nuances of language. It's like a master chef learning to create delicious dishes by studying countless recipes.
I'm starting to get hungry just thinking about it. So the model learns to understand language by devouring tons of text. But how does it actually learn from this data? How do we go from like a bunch of text to a model that can understand and generate language?
That's where the magic of backpropagation comes in. It's an algorithm that helps the model learn from its mistakes. Imagine you're learning to play a new instrument,
Okay.
and you keep hitting the wrong notes. Your teacher gives you feedback, helping you adjust your technique until you get it right. Backpropagation does something similar for language models.
So it's like the model has its own personal language tutor, gently guiding it towards fluency.
That's a great analogy. Backpropagation calculates the difference between the model's predictions and the actual target values, and then uses that difference to adjust the model's parameters. It's a constant process of trial and error, refinement, and improvement.
Okay, so we feed the model data, backpropagation helps it learn from its mistakes, and we repeat this process over and over again until the model becomes a language expert. Sounds pretty straightforward.
Well, it's a bit more complicated than that, but you've got the basic idea. Training these models requires a lot of computing power and time, but the results are truly remarkable.
Now, once we've trained this language model, what can we actually do with it? I know you mentioned text generation and translation before, but what other cool things can we do?
The possibilities are pretty much endless. One of the key concepts here is the idea of a foundation model. Think of it as like a Swiss Army knife of language models, capable of tackling all sorts of different tasks.
A Swiss Army knife. So we can use it to write poems, translate languages, answer trivia questions. What else?
You're on the right track. You can use it for things like sentiment analysis, which is like figuring out if someone is happy or sad based on what they write. You can also use it for named entity recognition, which is identifying and classifying things like people, organizations, and locations in text.
So the model can figure out who's who and what's what in a piece of text. That's pretty impressive.
It is, and it doesn't stop there. It can also be used for things like question answering, summarization, translation, language generation, semantic search, even zero-shot and few-shot learning?
Zero-shot and few-shot learning. Those sound really futuristic.
They are. Zero-shot learning means the model can perform a task it's never seen before just by being given a few examples or instructions. It's like learning on the fly. Few-shot learning is similar, but involves giving the model a small amount of training data for the new task.
So the model is learning to learn. It's becoming more adaptable and versatile, kind of like a language prodigy.
Exactly. Foundation models are truly a testament to the power of deep learning and the potential of transformers to revolutionize how we interact with language.
This is incredible. It seems like transformers are going to change the world.
They already are, in many ways. They're being used in search engines, chatbots, virtual assistants, and countless other applications. It's an exciting time to be studying artificial intelligence.
Okay, we've covered a lot of ground here. How transformers work, how they're trained, and the amazing things they can do. It's clear that these models are incredibly powerful. But there's one thing that's been bugging me. Some experts say that what transformers are really doing is compression. That by compressing language to predict the next word, they actually learn a lot about the structure of language itself. Have you heard that?
I have, and it's a fascinating perspective. It highlights the connection between transformers and information theory, which is all about understanding how information is stored, transmitted, and processed.
Information theory. That sounds pretty complex.
It can be, but the basic idea is actually pretty simple. When we compress data, we're essentially removing redundancy and identifying patterns. It's like packing a suitcase.
Yeah.
You want to fit as much as you can without wasting space.
So it's like the model is learning to pack a suitcase full of linguistic knowledge.
That's a great way to think about it. By compressing language, transformers are forced to identify the most important elements, the grammar, the syntax, the semantics that make language work.
Okay, I'm starting to see the connection. But this raises an interesting question. If language models are so good at compressing information, does that mean they're also good at understanding the world?
That's a really deep question, and there's no easy answer. On the one hand, language is our primary tool for describing and understanding the world. So a model that's good at processing language should have some understanding of the world, right?
Right, like if the model can understand the sentence, the cat sat on the mat. It must know something about cats, mats, and the concept of sitting.
Exactly. But on the other hand, language is just a representation of reality. It's not reality itself. There's a lot that gets lost in translation, so to speak.
Like trying to explain the taste of chocolate to someone who's never tasted it before. Words can only go so far.
Exactly. So while language models can learn a lot about the world through language, their understanding is ultimately limited by the data they've been trained on and the inherent limitations of language itself.
That makes sense. So it's not like these models are going to become conscious or develop their own independent thoughts and feelings anytime soon.
Not likely, at least not with our current understanding of how they work.
Okay, good to know. I'm not quite ready for the robot uprising just yet.
Me neither. But let's not underestimate the potential of these models. They're already changing the way we interact with language, and they're only going to get more powerful and sophisticated over time.
Well, we've talked about how transformers work, how they're trained, and the amazing things they can do. But I want to circle back to the problem these models were designed to solve. Why were transformers such a game changer? What did they bring to the table that previous models were missing?
Remember those older language models that struggled with varying sentence lengths, the ones that needed a fixed size input?
Right, the ones that were stuck in the tiny tweet world.
Exactly. Transformers were designed to overcome that limitation by introducing the attention mechanism, which allows the model to focus on different parts of the input based on their relevance. It's like having a reader who can adjust their focus, depending on the complexity of the sentence.
So it's like a reader who can, like, skim a news article quickly, but then slow down and savor the details of, like, a beautifully written novel.
Precisely. This dynamic attention is what allows transformers to handle the variability and richness of human language much better than those older models.
And this breakthrough came in 2017 with that paper titled, "Attention is All You Need," right? I need to make a note of that for my test.
That's the one. It was a real turning point in natural language processing
Yeah.
and paved the way for the development of the powerful language models we have today.
Attention is all you need. I wonder if that applies to life in general.
Maybe. But for now, let's stick to the world of language models. Speaking of attention, one of the key advantages of transformers is their ability to process information in parallel. This is unlike older models that had to process words one at a time.
So it's like having a team of readers tackling a text simultaneously, each focusing on a different part. That sounds a lot more efficient.
Exactly. This parallel processing, it helps the model understand those long-range dependencies between words. Even if they're far apart, it can see the whole picture, so to speak.
So that's how the model can connect like a verb to a noun that appeared much earlier in the sentence. It's like those connect the dots puzzles where you
Mhm.
see the image emerge only after you've connected all the distant points.
I like that analogy. It really captures how the attention mechanism helps the model see those connections across the entire sentence.
Okay, so transformers solve the problem of varying sentence lengths and long-range dependencies. But language is complex, and there's always another challenge lurking around the corner. What about the sheer size of a language's vocabulary? How do these models handle all those words?
That's a great question. Language models need to know a lot of words to be considered fluent. If we're talking about holding a basic conversation, a few thousand words might be enough. But for tasks like understanding scientific papers or legal documents, the vocabulary needs to be much larger, potentially tens or even hundreds of thousands of words.
Whoa, that's a lot of words. It's like trying to memorize an entire dictionary. How do we even store all that information in a model?
That's where those embedding matrices come in again.
Hmm.
Remember how we talked about each token being represented by a vector of numbers, its own unique code?
Right, those personality profiles for words.
Exactly. Those vectors are stored in a matrix, and the size of that matrix can get very large, depending on the size of the vocabulary.
So the bigger the vocabulary, the bigger the embedding matrix, and the more memory and processing power we need.
Exactly. That's why researchers are constantly working on ways to optimize these matrices to make them more efficient. One approach is to use subword tokenization, which we talked about earlier. By breaking down words into smaller units, we can represent a larger vocabulary with a smaller number of tokens.
It's like finding a more efficient way to pack a suitcase. You can fit more in if you break things down into smaller pieces.
Exactly. It's all about finding clever ways to represent information in a compact and efficient way.
It's incredible how much progress has been made in this field in just a few short years. It seems like the pace of innovation is just accelerating.
It is. And that's what makes this field so exciting. We're constantly pushing the boundaries of what's possible, and who knows what amazing breakthroughs lie ahead.
We've journeyed through this intricate world of transformers, explored how they learn from massive amounts of data, and even touched on that fascinating idea of language modeling as compression.
We've seen how these models are capable of capturing the essence of language, understanding those long-range dependencies, and even representing factual knowledge.
It's been an incredible journey. But before we wrap things up, I have one last burning question. If we could, like, peek inside the mind of a transformer, what would we see? What's going on in there at the deepest level?
That's a question that has captivated researchers for years. It's like trying to unlock the secrets of the human brain. Only this brain is made of algorithms and data.
So what are some of the leading theories? Are there any clues as to what might be happening inside that black box?
There are a few intriguing ideas floating around. Some researchers believe we'd see a kind of map of concepts where related ideas are clustered together, like a semantic atlas of the world.
So like Google Maps for concepts, you could zoom in and see all the words related to, like cat, for example, all clustered together in one area.
That's the idea. Others believe we'd see a vast network of connections, representing the relationships between words and ideas, like a giant web of knowledge.
Wow, so the model is weaving together all these intricate connections between words and ideas. It's like watching a spider spin an incredibly complex web, only the threads are made of information.
That's a great way to visualize it. And still, others believe we'd see something entirely different, something we can't even comprehend with our current understanding of intelligence, something truly alien and awe-inspiring.
That's both exciting and a little bit unsettling. It's like we've created these incredibly powerful tools, but we don't fully understand how they work or what they might be capable of in the future.
It's a humbling thought, but it's also what makes this field so captivating. We're exploring the unknown, pushing the boundaries of what's possible with artificial intelligence.
Well, on that note of wonder and mystery, I think it's time to wrap up our deep dive into the world of transformers and large language models.
We've covered a lot of ground, from the technical foundations to the philosophical implications.
We've seen how these models are changing the way we interact with language and how they're pushing the boundaries of what's possible with artificial intelligence.
And who knows what amazing discoveries await us in the future.
Thanks for joining us on this incredible journey. Until next time, keep exploring, keep learning, and keep asking those big questions. All right, so you've got this big machine learning test coming up, huh? Multiple choice, written answers, the whole shebang. And you're not just aiming to pass. Oh, no, you want to ace it.
Well, we're going to try to make these concepts stick in your brain, like
Yeah,
super glue.
exactly. You provided a stack of materials on classification and supervised learning, transfer learning. Really meaty stuff, gotta say.
Well, luckily I'm here to help us dissect it all. We got to find those aha moments, for your test answers.
Yeah, make them shine.
Exactly.
Let's dive right in.
Let's do it.
So the Wolfram text mentions how classification is like the bread and butter of machine learning. They use examples like figuring out if an email is spam or if a picture is a cat or a dog, stuff we see every day.
Right.
Why is classification such a big deal in machine learning?
Well, because it tackles a problem that's both incredibly common and surprisingly powerful. Basically, taking a bunch of data and then predicting what category or what class a new piece of data belongs to. Think of it like sorting your laundry socks in one pile, shirts in another.
Okay, so it's about putting things in the right buckets. Makes sense.
Right.
Wolfram uses that car versus truck example to illustrate it. And to make it even more digestible, they simplify things by only looking at the vehicle's weight.
Yeah.
So light vehicle, probably a car, heavy,
Right.
probably a truck. They even give us a visual, a dot plot on a number line. Awesome for visual learners.
Absolutely. And what's really neat is that Wolfram goes beyond just those data points on a line, and they introduce this probability curve, which is super helpful for understanding how classification actually works.
Okay.
Imagine it like a landscape. Low weight, you got a high car probability peak, like a mountain.
Okay, I can see it.
High weight, you got a truck peak. But in between, the
Yeah.
curve dips down. That's the uncertainty valley. It shows that classification isn't always black and white. Sometimes there's a gray area where the algorithm, it's less sure.
That visual is super helpful. I can already picture it in my head. So it's not just about being right or wrong. It's about how confident the algorithm is in its prediction.
Yeah.
That's got to be important for those multiple choice questions, where they ask for the most likely outcome.
Exactly.
Speaking of real-world examples, Wolfram takes us on a little historical detour with the Titanic dataset. Class, age, sex, survival. It's like a data-driven mystery.
It is.
What can we learn from this dataset that will help us crush the test?
Two big things. First, real-world data. It's messy.
Okay.
Wolfram points out that the age variable is missing for some passengers. Super common in real data sets. So for your test, remember that data preparation, like cleaning it up and handling those missing values, that's a crucial step.
Makes sense.
Second, the Titanic data highlights this idea of feature importance. Wolfram shows that being female was a huge factor in survival, like massively increased your odds. We might intuitively guess that, but the data proves it. Understanding which features really drive a classification model's predictions, that's gold for those written response questions.
Right. And speaking of understanding predictions, Wolfram throws us a curveball. They tell us their Titanic classifier has 77% accuracy. Not bad, right?
Yeah.
But then they bring up this whole baseline thing. I have a feeling this is going to be important.
It absolutely is, especially for multiple choice questions that try to trick you.
Oh, no.
See, if you just guessed randomly survived or died, you'd have a 50-50 chance of being right.
Okay.
But because more people on the Titanic died, always guessing died would give you 61% accuracy.
Wow.
Suddenly, that 77% doesn't seem as impressive.
Whoa. Okay, so it's not enough to just look at the accuracy number. You got to compare it to what you'd get by just guessing blindly or using a simple rule. It's like in baseball, a .300 batting average is great.
Yeah.
But not if everyone else is hitting .4000. Context is key.
Exactly.
Let's switch gears for a second and talk about transfer learning. Wolfram uses a mushroom classifier as an example, and that Medium article really dove into it too. Imagine trying to train an image classifier from scratch. That'd be like trying to bake a cake without a recipe, right? Total disaster waiting to happen.
Exactly. Transfer learning is like using a pre-made cake mix. Someone's already done the hard work of figuring out the core ingredients and the basic steps. You just add your own special touches like frosting or sprinkles to get the exact cake you want. Think of it this way. Someone else trained a model on a massive data set of images, teaching it to recognize basic features like edges, shapes, textures. That's your cake mix.
I like it.
In Wolfram's example, they take a pre-trained model that's already good at seeing, and they use it as a starting point for their mushroom classifier. They just add a few extra layers on top, that's the frosting, to make it specifically good at telling different kinds of mushrooms apart.
Okay, so it's like building with Legos. You don't have to start with individual bricks. You can use pre-built sets and just add your own custom pieces on top. That's way more efficient, especially when you're dealing with something as complex as image recognition. But hold on, that Medium article mentioned something about memory issues. Even with fine-tuning these giant models, that's where Laura swoops in to save the day, right?
Oh, no, there, got it. Laura is like a memory wizard, helping us deal with these massive models without needing a supercomputer. Imagine you have a giant, detailed image file. Laura is like a compression tool that finds the essential information and stores it much more efficiently, like creating a smaller file that still captures the key details.
Okay.
The visual they use, breaking a big matrix into smaller pieces, is key here. Laura uses these things called low-rank matrices to represent the same information with fewer numbers. It's like finding a shortcut to express a complex idea in a simpler way. And then there's QLaura, which takes it even further. It's like compressing the already compressed files, same info, even less space.
All right, so we've got Laura as our memory-saving superhero and QLORi as its even more efficient sidekick. This is great stuff, but I think we need to pause here for now. And
Let's pick up where we left off. You're doing a great job connecting these concepts, and I can already tell you're going to rock that test.
thanks. I'm starting to feel a lot more confident, but before we move on, I want to make sure I'm crystal clear on something.
Hmm.
We talked about baselines for accuracy, but Wolfram also mentioned likelihood. It sounds kind of similar, but I'm not sure I get the difference. Can you clear that up for me?
Of course. Likelihood is another way to evaluate how well a classification model is doing, but it goes a step further than just being right or wrong. Remember those probability curves we talked about?
Mm.
How classification often involves some uncertainty? Well, likelihood factors in how confident the model was in its prediction. It's not just about hitting the target, it's about how close you were to the bullseye. Imagine the model is looking at a mushroom and trying to decide if it's poisonous or not. If it says poisonous with 99% certainty and it's right, that's a high likelihood outcome. But if it says poisonous with only 51% certainty and gets lucky, the likelihood is much lower, even though it made the correct classification.
Ah, okay. I see the distinction now. It's like the difference between a student who's totally sure of the answer and one who's just taken a wild guess. They might both get it right, but the one who's confident is showing a deeper understanding. So for the test, I should keep in mind that both accuracy and likelihood are important ways to measure how well a model is doing.
Exactly. Each one tells us something different. Now let's go back to the Wolfram text for a minute. They make this interesting point about transfer learning and structured data. Things like bank transactions or customer information, all neatly organized in rows and columns. Apparently, transfer learning isn't used much with that type of data.
Yeah.
At least not yet. Why is that?
Yeah, that surprised me too. If it works so well for images and text, why not apply it to other kinds of data?
Well, the catch is that structured data is often very specific to its own little world. Unlike images, which have universal elements like edges and shapes, or text, which follows grammar rules, structured data tends to be very context dependent. Think of a model trained on bank transactions. It's learned patterns related to spending habits, maybe fraud detection, stuff like that. Now you try to use that same model to predict customer churn for a telecommunications company. Totally different features, different relationships between the data. Direct transfer learning isn't as effective because those two worlds don't have as much in common.
So it's like trying to use a recipe for baking a cake to build a house. The ingredients and the steps are just too different, even though they both involve creating something. But hold on, Wolfram said transfer learning isn't used much for structured data yet. Do you think that could change in the future?
That's the million-dollar question. If researchers can find a way to represent structured data in a more universal, abstract way, capturing underlying patterns that go beyond specific domains, then transfer learning could revolutionize how we analyze all sorts of data.
Interesting. It's like finding a universal language that lets different types of data talk to each other.
Uh,
Okay, I'm making a note of that. Future of transfer learning.
yeah.
The structured data revolution has a nice ring to it.
Yeah.
But before we get too carried away with the future, let's bring it back down to earth for a sec. We still haven't touched on that third article about Laura and QLaura. I remember it mentioned something about low-rank matrices. Can you remind me why those are so important?
Absolutely. Remember we talked about Laura being like a file compression tool for those giant models? Well, low-rank matrices are the secret sauce. Think of a matrix like a grid of numbers. In many machine learning models, these matrices can get huge, thousands or even millions of rows and columns. Storing and processing all those numbers takes a ton of computing power and memory. Now imagine you could express the essential information in that massive matrix using a much smaller set of numbers. That's what low-rank matrices allow us to do. It's like taking a long, complicated story and condensing it down to the key plot points.
So it's like creating a SparkNotes version of a super dense textbook. You get the gist without getting bogged down in all the nitty-gritty details. But how does Laura actually use these low-rank matrices?
Great question. Laura leverages these low-rank matrices to represent the changes made during fine-tuning. Remember we talked about adding those extra layers, the frosting, to a pre-trained model? Well, Laura figures out how to capture those changes using a much smaller set of numbers, like a really efficient set of instructions. It's like adding a small, targeted update to the original model instead of rewriting the entire thing.
So instead of rewriting an entire textbook, you just add a few sticky notes with your key insights.
Yeah.
Makes sense. Now, I vaguely remember the article mentioning QLoRa as well. How does that differ from regular LoRa?
QLoRa takes this idea of memory efficiency to an even higher level. Remember those low-rank matrices we were talking about? Well, QLoRa applies a technique called quantization to them. It's like taking those SparkNote summaries and condensing them even further, using abbreviations and shorthand to convey the same information with even fewer words.
Okay, so QLoRa is like the ultimate note-taking hack, getting those complex machine learning concepts down to their bare essence. Perfect for someone like me, cramming for a test with a brain that's already overloaded.
You got it. Both LoRa and QLoRa are essential tools for making large language models more manageable and accessible, especially when you're fine-tuning them for specific tasks. And speaking of your tests, let's make sure we're connecting these ideas to those potential exam questions. Remember, understanding the why behind these techniques is just as important as knowing the what.
That's great advice. I'm feeling a lot more prepared to tackle those tricky written response questions now. So to recap, LoRa and QLoRa are all about shrinking those memory-hungry models down to size, like creating super efficient study notes for a machine learning prodigy. And I can definitely see how that would be crucial when you're dealing with models as massive as GPT-3. But I think we need to pause here for now. And all right, we're in the home stretch now. We've covered a ton of ground: classification, baselines, likelihood, transfer learning, even those memory-saving tricks like LoRa and QLoRa.
It's been quite a journey.
It has. But before we wrap up, I want to make sure all of this is really sunk in for you. It's test day, you're sitting there with the exam in front of you. What are some of the key takeaways that pop into your head? Those aha moments that'll help you nail those questions.
I think you've done a fantastic job of that. You've really grasped the importance of context and classification. It's not enough to just know the definition or the algorithm. You need to understand the nuances of the data, the baselines for comparison, and even the potential biases that might be lurking beneath the surface.
Yeah, that whole baseline thing was a real game changer for me. It's so easy to get caught up in a seemingly impressive accuracy number, but without a proper baseline, it's meaningless. Like, knowing a stock went up 10% is only useful if you know where it started, right?
Yeah, exactly. But you've also shown a great understanding of the trade-offs involved. We talked about accuracy versus likelihood. Sometimes you might prioritize one over the other depending on the specific problem you're trying to solve. And with transfer learning, you've grasped the power of leveraging existing knowledge, but also the limitations when dealing with data that doesn't quite fit the mold.
It's all about choosing the right tool for the job,
Yeah.
just like a chef wouldn't use a spatula to chop vegetables. But speaking of tools, I'm curious, how do you think about these concepts? Do you have any mental models or analogies that help you make sense of it all?
Well, I tend to be a very visual thinker, so I often rely on spatial metaphors. For me, a machine learning model is like a complex landscape with peaks and valleys and plateaus. The training process is like exploring this landscape, searching for the lowest points those represent the optimal solutions. When it comes to things like LoRa and QLoRa, I think of them as sculptors, chiseling away the unnecessary parts of a model to reveal its most efficient form.
I love that analogy. It's like those marble statues where you can see the artist's skill in every curve and detail. It reminds me that machine learning isn't just about cold, hard numbers. It's about finding patterns and meaning in the data. It's almost like being a detective, piecing together clues to solve a mystery.
That's a great way to think about it. And the more we understand these concepts, the better equipped we are to use them responsibly and ethically. Machine learning is a powerful tool, and it's up to us to wield it wisely.
Couldn't agree more. Well, I think this deep dive has given me not just the knowledge, but also the confidence to approach my test with a fresh perspective. I'm not just memorizing facts, I'm understanding the core principles and seeing how they connect to the real world. And for anyone else out there facing a machine learning exam, remember stay curious, ask questions, and find those aha moments that make the concepts click for you. That's what true learning is all about. Thanks for joining us on this deep dive into the fascinating world of machine learning classification. Until next time, keep exploring, keep learning, and good luck on that test.